Hi, I'm Julien. I'm going to present our work on model robustness inspired from style transfer techniques. So robustness is crucial for safety-critical systems such as a self-driving car. Of course, the end user wants the car to behave good in all kinds of weather conditions, in all countries, from day one to the end of life of the car. So here, we don't focus on robustness toward adversarial attacks, even though this is a very important topic, but we rather focus on anything that could disturb the sensor signal. Under the roof of such systems, we use DNN, and to be trained, it needs a lot of data. To achieve a good robustness toward various conditions, we tend to enlarge the training dataset. However, it costs a lot, takes a lot of time, and this is somehow a kind of endless effort because during the entire life cycle of the product, the system will face so many conditions that cannot be gathered in a dataset. Under the roof of such system, we use DNN, and to be trained, it needs a lot of data. To achieve a good robustness toward various conditions, we tend to enlarge the training dataset. However, it costs a lot, takes a lot of time, and this is somehow a kind of endless effort because during the life cycle of the product, the system will face so many conditions that cannot be gathered in a dataset. Some data augmentation mechanism, more or less complex, can be employed to improve generalization, but it requires a good knowledge of the sensor, such as the sensor model. This is a kind of standard practice in computer vision, but it turns out to be complex and not efficient for other sensors, especially active sensors such as radar, ultrasonic, laser scanner. In our work, we aim to improve robustness using sensor agnostic methods so that it can be generalized on any kind of sensors, no need for sensor model, and any kind of task, no need for semantic segmentation mask. A robust system is able to have its prediction unaffected by perturbation on the input data. In our study, perturbations are any kind of noise that could reflect a sensor edging, different weather, or lighting conditions. Whatever is the perturbation, the object we intend to detect is still there, only somehow the style of the image differs. Here, we make the analogy with style transfer, where the objective is to transfer the style of an image into the image under test without modifying the structural information, that is to say the content. In this example, when applying different styles to the image under test, the content information on the style modified image is still very similar. This leads us to think that by enforcing a model to learn only the content and discard the style information, we can achieve a better level of robustness. The amount of style information is measured by the gram matrix. This is a correlation between the channel of the feature map. It somehow reflects the relationship between channels like a texture measurement. We introduced a style layer, which acts as a residual connection. The objective is to attenuate the feature map that carries the style information so that the model can learn only useful information. A StyleLess layer is a sequence of 3 convolution ReLU layers. First and last convolution have a kernel size of 1 by 1 to compress and decompress channel-wise. The second convolution aims to learn connection, relationship between filters, very similar to what a gram matrix would do. StyleLess layer acts at the feature map level. We have designed a new loss function, we call it gram loss. It measures the difference of information between the input and output feature map of the StyleLess block. The gram loss encourages each of the StyleLess blocks to attenuate the style information. The training protocol is straightforward. First, the model is trained for its task using its own loss. Then, once trained, that is to say feature map include both style and content information at that stage, we now activate the style layer and fine-tune the entire model with a new loss that combines both the task loss and the gram loss. If we look more in detail, on this example under running condition, we can see that the StyleLess layer tends to suppress information that does not really look meaningful, like a lot of noise, while it preserves useful information located, for instance, around the object, such as the edges of the vehicles. We evaluated our contribution on 2 key driving tasks, on semantic segmentation and object detection. For both of them, we used Cityscape dataset for the training and validation, And we included a noisy version of Cityscape inspired by the work of Kaman and Hall, Painting by Number. So it applied 15 noise model over 5 intensities, that is to say 7000 plus images. For the segmentation task, we use DeepLab v3 as a baseline. Most of our evaluation has been performed using ResNet 18 backbone because hardware capabilities are limited in the automotive industry. So we focus on architecture that reflects the most what can be embedded on this hardware. We evaluate StyleLess in comparison with the data augmentation mechanism introduced in the work of Kaman and Hall, Painting by Number. It has been designed specifically for semantic segmentation tasks as it requires a segmentation mask, but it cannot be applied to other tasks nor other sensor modalities. Results for ResNet 18 are depicted in this table. StyleLess layer achieve in average better performances over the baseline and Painting by Number. We also stress that the gain does not come from the few added residual blocks that underperform the baseline without the gram loss. Finally, evaluated on the corrupted dataset, the StyleLess version of ResNet 18 even outperforms on some noise variant ResNet 50, which has more than twice parameters. We illustrate result images on few noise variants. To demonstrate the versatility of the StyleLess layer, we applied it on another task and another backbone. Again, for hardware limitation constraints, we selected SSD for object detection task using VGG backbone. We benchmark our approach with Advent, an unsupervised domain adaptation approach. Even if StyleLess is penalized compared to Advent because it does not see during the training phase the targeted domain, fog or rain, it still slightly outperforms Advent. To summarize our contribution, we introduce a new StyleLess layer that enables to learn robust representation. It reaches substantial gain on corrupted data, including adverse weather conditions. It does not require specific data label and can be applied on any sensor modalities as it acts on the feature maps.